Hi, good morning students. So today we will discuss about example number 2.7. In the last clips we have discussed about some of the examples of chapter number 2nd. Right now we will deal with the chapter number 2nd's another example that is called as example number 2.7. Right now you have been given such type of terms. The student measures the thickness of a human hair by looking at it throughout the microscope, and its magnification is 100. So first of all we are mentioning all those data which is given to us, that is called as a magnification. Magnification is denoted by the small symbol m, that is called as 100, and he is observing n number of observation, that is called as a number of observations. This is 20. Now we have to find it out. The average width of the human hair with the microscopic view which has been observed is 3.5. What is the estimated thickness? So we have to find it out. Estimated thickness of human hair, and that is what, and we have observed thickness, that is 3.5 millimeter. So as on now our data has been given to us, that is 3.5 millimeter. So whenever such type of observations are that put such type of observation, that is called as observations thickness, and that is called as divided by estimated thickness. So we can just say that m is okay. Our observed thickness is 3.5 millimeter, and that is called as estimated. So we can have estimated equals to 3.5 divided by m. So our estimated thickness is equals to 3.5 millimeter divided by 100. So we can have our estimated thickness of a human hair is 0.035 millimeter. So this is the very practical type of examples. So whenever they are asking you such type of example, and solve with the help of such as the formula. Actually such type of 3 or 4 formulas you will use in practicals, but right now whenever you have a magnification, it is called as a real and apparent observations. So in some of the examples we will also use such as the this formula. Now you have been given that answer the following. First of all, we have a 3 different type of questions in front of us. You are given a thread and a meter scale. How will you estimate the diameter of a thread? Whenever you have, let's say I have to find it out the diameter of it, I'm just putting and just making number of tons over that. So I can have my diameter is equals to length divided by number of tons, and this is how I can find it out my number of observations by using such formula. And that is why just using my length of a scale and number of tons over there, just taking the ratio of it, and it will give me the diameter. So that is quite simple one. Next one is called as a screw gauge has a pitch of 1 millimeter and 200 divisions are there on the circular scale. Whenever you will learn about screw gauge and meter gauge and vernier calipers, you will learn about such type of patches and number of scales on a. There are 2 type of scale. One is called as a stable scale, and on a screw gauge that is called as a rotating or circular scale. So you have to find it out to increase the accuracy of a screw gauge with the help of any data given to you. So first of all, whenever such type of possible increment in accuracy for the screw gauge, so you are aware about its a formula that is called as a least count is having the formula. In last clip we have discussed about this formula. It is called as a least count, LC. It is called as a pitch divided by number of divisions. You can directly observe that whenever your ratio of denominator, or you can say ratio, is higher, your answer is lesser than 1. So you have 200 divisions given to you over here, that is called as a 200 divisions you have. So if I will increase instead than 2000, then my answer is lesser than 1, very much lesser than 1. So compared to 200, compared to 2000, my answer is very much lesser in 2000. So you can say that by increasing number of divisions, I can just increase my accuracy. Next one is the third one. In the third one, you have been given that the mean diameter of a thin brass rod. A brass is a combination of your aluminum, copper, and such type of thing you will learn in chemistry. Such type of combinations are there, and it is by measured by the vernier calipers. We can just set that 100 measurements, and diameter is expected to yield a more reliable estimated than the set of 5 measurements. Means you are taking two observations. One is called as a 5 observation, and next one you have 100 observation. Always keep in mind, and that is I am always mentioning to the students, that if you will take more and more observation, you are coming near to very much accurate value. So you can say that ratio accuracy is having direct proportional to number of observation. If you are if you are in a need of a higher accuracy, so just go and just find it out more number of observation. So this is the quite simple formula. So you can just increase the your accuracy by increasing the number of observation. This is the primary relationship we have drawn from such type of data given to us. Now next one is called as our example number 2.7 sorry 2.9. In the 2.9 you have been given this is the data in front of you. Let's say a photograph of a house occupies an area of a 1.75 centimeter square, and it's a sliding of 35 millimeter slice. So first of all, I'm just saying that my data for the given part is called as my object's area. It is occupying the area of a 1.75 centimeter square, and it is projected at a 35 millimeter slide on, you can say, projector. So first of all, I'm just using that at 1.75 centimeter square, and projected on the area of the house on the screen. It is called as its image area. It is a 1.55 meter square. Your this much data is in meter and this is in the centimeter. So first of all, either convenient way to convert either one of them in a centimeter or in a meter. So I'm taking that 1.75 10 to the power minus 2. It is meter and it's a square. So I can have a 1.75 cross 10 to the power minus 4 meter square. This is my first conversion I have. Next one is called as my image would be there. I have to find it out my magnification. They want two magnification, normal magnification and linear magnification. So in a previous example, we have already in a 2.7 we have already used this formula. It is called as a magnification is called as a area of image and divided by area of object. You can also remember like that the previous one and the last one, that is called as a ratio of the latest and the previous, it is called as a magnification. So my image area is called as a 1.55 meter square, and my object area is a 1.75 10 to the power minus 4 meter square. Unit can be cancelled out. So my magnification I have received is 10 to the power minus 4 is going in a numerator, is 10 to the power 4. So I can get 0.008 0.8857. So my magnification is 8857. You can remember that magnification or ratio of any physical quantity does not give you any unit. So this is unitless quantity. Basically we are habitual or always make a habit that your answer must be in the terms of unit, but this is actually unitless quantity, so we are not putting any type of unit over here. Next question in the same task is given to us is that called as a find out linear magnification. You are aware that my area is having relationship with the length square, so I can say that L is a proportional to areal part, so that is called as a linear magnification is equals to under a root of a areal magnification. It is called as the area's magnification is in the square root having relationship with the linear magnification. So my linear magnification is equals to under root of aerial magnification. We have found it out. It is called as 8857. So this would be my linear magnification is 94.11 meters, because it is called as a linear magnification. So ideal way is that a linear magnification is 94.11. Now what they want is that they want that in the terms of, let's say I am asking or adding one more question, find out your answer with the more and more significant number. So in the term you can see that your data having three significant digits. This one contains 2, this one contains 3. So you can be careful that whenever you have a such type of significant digit, they want whichever number contains the least significant digit, that we will follow. So you can say that 35 means 2 significant digits are there, though they haven't asked in this question, but you can write down your answer in terms of least significant digit. So our answer for the linear magnification is 94.11, and for the normal magnification or aerial magnification is 8857. In the next one, they have asked us this example we have already done when we have just discussed about the significant digits, though we will just solve it out because it is given right now for the sequence examples. So we have to find it out how many significant digits are there in this much numbers. So it is example number 2.10. As per our rule, previous zeros are not considered and there is only one significant digit. 10 to the power is not considered. All the non-zero digits are significant digits, that is why 3. If our number is less than 1 and last 0 is there, or that would be a decimal point, we will not consider the previous 0, we will consider last 0. So we will have a 4 significant digits. But be careful, we have also discussed about some of the tricky equation when we have discussed about our significant digits. Instead of 0.2730, if our number would be given, that is called as a 2730, then we will not consider last 0. So keep in mind, right now we have a 6.320 decimal point is there, that is why we will consider that 0. 0 is preserved between two non-zero digits, that is why it will considered. 0 is there but it is preserved between two non-zeros, and then previous zeros are not considered. So right now in this case we have 4 significant digits. So this is how you can solve such type of example. Right now example number 2.11, we have already done such example. You can be given that the length, breadth and the thickness of the rectangular sheet, having that the length is 4.234 meter, then breadth is 1.005 and your thickness is called as a 2.01. So you can have all those data. Apart with that, we have to find it out its area and volume. So calculation I am giving up to you, and first of all L, B and let's say H. My length is of 4.234 meters. My breadth is 1.005 meters and my thickness is a 2.01 centimeter. So I am converting this centimeter into meter, so I can have a 0.0201 meters. So I have all those data. Right now I want to find it out my area. So area of a rectangular sheet is twice times of LB, BH and HL. I am putting all those values over here for you. So twice times 4.234 into 1.005 plus 1.005 into 0.0201 plus 0.0201 into 4.234. So just calculate it out and you are aware that it is area, so it's a unit is meter square. So all our data is having unit meters. Now I want to find it out my volume. So volume would be, I can have L, B and H. So I'm putting all those values over here. So my length is 4.234 into 1.005 and then 0.0201. So you are aware that whenever there would be a volume, it is having the unit meter cube. So with the help of calculator, you can calculate such type of data. So I am just leaving up to you. So find it out area of it and the volume of it. Now example number 2.12. In the 2.12 we have been given such type of data. You have been given one pendulum, and in this pendulum the mass or mass of balance box is a 2.300 kilogram. Apart with that, two gold pieces of masses 20.15 kilogram and 20.70 gram added to this box. We have to find it out total mass of this box and what will be the difference of the pieces into the box. We have to find it out difference and as well as total mass. First of all, I'm just taking that box's mass. Let's say I'm just mentioning it as a M1. It would be 2.300 kilograms. My box contains two pieces of gold. It is having 20.15 gram. So our ideal way is to convert into terms of either convert 2300 in a gram or maybe this one in a kilogram. So I'm just using 0.02015 gram. I have another data that is called as a 20.17 gram. So 0.0217 gram. So this is my data. I have to find it out total or net mass. So I am taking that addition of all. So right now I can just give that total M, that is 2.3. Because of the last two digits I am just neglecting. 0.02015 plus 0.0217, all are in terms of gram. So I can have a capital M, that is called as a 2.34032 kilograms. Sorry, all my data is in a kilogram. So this is also in terms of kilogram. Now I want to find it out with the significant digit. You can say that list significant digit, that is 2.3, which contains only two significant digits because our number is more than one. So my mass with the significant digit is a 2.3 kilograms. You might be wondering that my box contains weight 2.3 kilogram, with the significant digit it will be mentioned as a 2.3 kilogram, and after adding such type of data to or mass to it, it will also give me 2.3. But the thing is that with the pure and pure accurate number, we are right now very much near to our actual answer. This is our actual answer with significant digit. So always keep in mind that significant digits advantage is like that. Now second task is that we have to find it out difference between the masses. So there is a difference between the masses. So I'm just naming it as m dash. It is called as m2 minus m1. So I can have m dash, that is why I have values that is called as 20.17 minus 20.15. So my m dash equals to 0.02. All this data it is in the terms of gram. So I haven't converted this one in the terms of kilogram, as I have mentioned it this were in kilograms. So now next one, this is the example we have done. So many examples of such category. We have the percentage error of a measurement in A, B, C and D are 1%, 3%, 4% and 2%. So I can just say that delta A by A in terms of a percentage is a 1%, delta B by B it is a 3%, delta C by C it is a 4%, and delta D by D is equals to we have 2%. and they have given us that equation. Our equation is that P is equals to a cube b square c raised to 1 by 2 and d. So first of all, I am just converting this expression in very simple manner. Under root of a c and d, as per our notation suggests us, that is called as a delta p by p is equals to 3 times delta a by a, 2 times delta b by b, 1 by 2 times delta c by c, and only d by d. So I can have all those data available to me in terms of percentages: 3 into 1%, 2 into 3%, 1 by 2 into 4%, and only 2 percentages. So I can have a delta p by p, that is a 3 and 6, 9, 9 and 2, that is called as a 2, and 3, that is called as I have 13%. It is the error in a measurement of p. So this is very simple example, but we have done plenty of examples of our errors and measurement. Now 2.14 is again good example. In some of the school exams, they are just asking you such type of example to verify that our equation is valid or not, or it is called as a homogeneity of expression. So this is a new thing for you. Always such type of examples can be solved with the help of homogeneity. You might be aware about homogeneity. The homogeneity is called as our left hand side and right hand side both must be equal. If both must be equal, then it is called as a homogeneity. So right now we will just use such type of expression, that is called as our homogeneity expression. We have been given such type of data. Very first thing is called as a y equals to a sine 2 pi by t. Next one is this one, and these are the examples. More important thing we have to consider whenever we are solving such type of examples are this data, which is called as a maximum displacement. Basically, whenever a will be there, we will use that, or we are habitual to our secondary schooling that a is acceleration, but here they have mentioned that a is maximum displacement. V is called as a speed. You will gradually learn that in our textbook. Whenever there would be a frequency, they have used such type of symbol, so sometimes we will be quite confused. Then we have capital T. It is right now not visible, so I'm mentioning and boldening it. So capital T is called as a period of time, and small t is basically time, so I'm mentioning that a t is called as a time. So I'm just solving this example, and you are aware that all contains left hand side equal, so I'm just putting that all contains left hand side equal because they have mentioned that a y, so I'm mentioning common left hand side for all. It is called as a y. It is basically length. It is having dimensional configuration. Left hand side contains L1. Now right hand side of a first one. So in the right hand side of a first one, you will be seeing that it is containing small a sine 2 pi t upon capital T. As we are habitual that sine is a trigonometric function, so it is neglected. 2 pi is a number, again neglected. T is time, it is containing unit second or t1. This t is also containing unit time second t1, so both will be cancelled out because of the same unit. So we have only left part is called as a, and they have mentioned that a is a displacement, so its dimensional configuration is L1. So in the first one we can say that the left hand side and the right hand side both are equal. So very first expression is a true one. Next one is that we have been given that y is equals to a sine vt. So we are only discussing about right hand side because the left hand side we have already calculated. A is called as a displacement. I am putting as it is. Sine is called as a mathematical function. It does not contain any type of unit or dimensional configuration. V is basically given as a velocity, so I am putting it as a unit meter per second, and t is called as a time, it is called as a second. So I can have this is displacement, this is also meter, so I can have my unit meter square. so I can have L2. So it is not matching with my left hand side. So left hand side and right hand side are not equal. So homogeneity is not maintained. So this is the wrong expression. Third one, having right hand side, that is called as a small a by t displacement upon time and sine t divided by a. I am neglecting sign. So you can say this is second, this is second, this is meter, this is meter. It does not contain any unit. So M0, L0, T0. Again, our left hand side is not equals to right hand side. So equation number third one is wrong one. Fourth one is containing right hand side. So I'm mentioning that fourth one is containing right hand side is called as A multiplied by root 2 sine 2 pi t by t and plus cos 2 pi t by t. Now you can see that sine and cos, when we are finding it out, it is called as a limitation of dimensional configuration. If I will give you that recall that whenever we have discussed about our dimensional configuration, I have told you dimensional configurations are not valid for the logarithmic function and trigonometric functions. So this is trigonometric function sine and cosine. So I am not using at all. 2 pi is number, again constants are not having any type of unit. Same is the course for the time. Time is cancelled out, again time is cancelled out. So this entire quantity is unitless. This is also unitless. This one is a number. Number is actually unitless. So only left part with us is called as a. And A is called as a our displacement. So its dimensional configuration is L1. So you can say that it is matching with the right hand side. So this is the true one. So our formula is true. So how you can calculate? I have just shown you the method. This is the very ideal method. With the help of this method, you can find it out all those formula which are true or wrong. So have a practice of this one. 2.15 number example is very much curiosity type of example. A famous relation in a physics which has been founded out by the moving mass. We have in physics there are different type of mass. It is called as a moving mass. It is only applicable to the small particles. So my moving mass is m and my static, or it is called as a rest mass, it is called as a m0. This is the first expression. This is the expression which has been derived by a world famous scientist Sir Albert Einstein. So this is the formula we have. We have to a student recall this expression but forget one physical quantity which is called as a c. You are aware that c is called as a velocity of light in vacuum and v is normal velocity we have. So a boy forgot to place c somewhere in this expression. So we have to find it out where we can place this expression. So first of all, I am mentioning this formula for you. M is equals to m0 1 minus v square. It's a square root will be there because it has been placed with the power of a 1 by 2. As per our homogeneity, I am following left hand side equals to m. It is having unit kilogram. So its dimensional configuration is m1. If this expression is true, as they have mentioned that this is the expression which has been derived by Sir Albert Einstein. So left hand side and right hand side both will be equal. It is actually mentioned. So we want that this entire right hand side will be real one. If I am putting c over here, then it would be kilogram meter per second. So this is not valid. If I am putting over here, then again in denominator which will contain the same unit. As we have discussed in the previous clips that whenever we are going for the addition or subtraction, our dimensional configurations must be same. And if I am putting c over here, then it will contain unit meter per second. It is also not valid. So but if I am imagining that I am putting c over here, means velocity having unit meter per second, and this one is also having meter per second, so it may give me something hopeful. So I am using that. 1 minus, it is a v square, so I'm putting that meter per second square, and I'm putting that c over here, it is also containing the same unit, so this is cancel out, so my denominator is unitless, my numerator contains unit, then and then it is containing kilogram, and then it is m1, so I can write it down that my real expression would be this one. It is called as m0 divided by under root of 1 minus v square by c square. So students, you can place the value of a c at different points and just calculate logically, okay, where you can place the value of c, then your equal expression can be, or homogeneity must be maintained. So this is the very simple method and a very good example for your measurement of common sense. Now we have example number 2.16. In a 2.16 example is a good example because of some of the chemistry's calculations are also there. You have been given that a unit of length convenient to atomic scale is an angstrom, and you are aware that 1 angstrom equals to 10 to the power minus 10 meters. The size of hydrogen atom is 0.5 angstrom. Size of atom. Remember, whenever size of atom is given, it means that they have been given you radius of atom. It is called as a 0.5 angstroms, and you are aware that 1 angstrom equals to 10 to the power minus 10 meters. So I can have a, this is my radius available to me. Now you are aware that atom contains the shape. Atoms containing spherical shape, that is called as a sphere shape. So its a volume would be 4 by 3 pi r cube. So I am putting all those values, 4 by 3, 3.14, and my radius is a 0.5 cross 10 to the power minus 10. It's a cube. So whenever you are calculating, always keep in mind that your power would be calculated first. So 4 multiplied by 3.14 multiplied by 0.5, again 0.5, again 0.5, divided by, we have 3. So we can get our data, that is called as a 5.234. I have just taken one more advantage of power. Then previously my power was minus 30. I have just placed one more point, and that would be 5.234 cross 10 to the power minus 31. That is called as a meter cube. Now I want to just find it out, its actual number of moles or area. I want to just find it out, it's a total atomic volume. So always take a Avogadro number. The value of Avogadro number is called as 6.023 cross 10 to the power 23. So Avogadro number, I am putting that 6.023 cross 10 to the power 23. So my now volume would be, atomic volume would be 6.023 10 to the power 23 multiplied by 5.234, again multiplied by 10 to the power minus 31. So my actual atomic volume would be, I received over here directly, 3.152 cross 10 to the power minus 7 meter cube. This is the my volume I have been assigned to me. So I have calculated and already calculated all those data. So whenever you are calculating such type of things, have your calculator handy with you. Now another example, it is a 2.17. Here you have been given that 1 mole of ideal gas of a standard temperature and pressure, and that is called as a V volume at STP. So this is your volume, and that is called as a molar specific volume. So I'm just mentioning that it is called as a molar volume. It is 22.4 liters. So keep in mind, in physics we are having 1 liter equals to 10 to the power minus 3 meter square. So my molar volume is equals to 22.4 liter has been converted to meter 10 to the power minus 3 meter square, sorry, meter cube. It is a volume, that is why meter cube. And then my size of the hydrogen will be 1 angstrom. Quite it is not visible, but it is actually 1 angstrom. So as per previously they have also given you the size, means it is called as a radius. We can just find it out. So I have a radius equals to diameter divided by 2. My diameter is called as a 1 angstrom divided by 2. So my radius is a 0.5, 10 to the power minus 10 meters. My volume would be 4 by 3 pi r cube. I have all those data available to me, so I am just directly placing all those data. So my volume after this calculation would be 5.234 cross 10 to the power minus 31 meter cube. And you are aware that whenever we are finding it out, our atomic mass or atomic volume, we have to multiply with Avogadro number. Avogadro number multiplied by volume is giving me that V dash. It is called as atomic volume. So I am just multiplying both those things. So my V dash would be 5.234 10 to the power minus 31 multiplied by 6.023 cross 10 to the power 23. So I got that my atomic volume would be 3.152 cross 10 to the power minus 7 meter cube. I found it out both, but in our example they have asked us to find it out that ratio of both. What is the ratio of molar volume and our atomic volume? So ratio they want is called as our molar divided by atomic. So my molar is available to me, just right beside it. It is called as a 22.4 cross 10 to the power minus 3, and divided by my atomic is 3.152 cross 10 to the power minus 7. So minus 7 is going in numerator, that would be 10 to the power 4, and this is the ratio of 7.1. So this is called as a ratio of molar and atomic. So this is the thing they have to they have asked us to find it out. And one more thing they have asked us, that why is this ratio so large? Because whenever compared to the normal single 1 mole at STP is something different compared to our atomic mass. That is why both are different things. So whenever in chemistry you will learn about such type of data, be careful. Molar is something different and atomic something is something different. So the ratio is somehow you are receiving compared to their actual values, somehow larger one with power of 10 to the power 1 and a higher one. So in next clip we will discuss about the remaining examples. Thank you.